Welcome to Evo AI, where we navigate the intriguing evolution of artificial intelligence. I'm your host, Bogdan Yanku, and in this series, we'll explore how artificial intelligence is transforming the way we work, innovate, and grow. From small startups to corporate giants, we'll unravel the mysteries of AI, uncovering insights, strategies, and the real-world impact on our everyday lives. Whether you're in sales, finance, marketing, human resources, or just curious about artificial intelligence, Evo AI has something for you. Hello, listeners. Welcome back to AI Unlocked. In today's episode, titled AI From Prompting to Music, we'll explore the relationship between music and technology. Before we begin, just allow me to quickly remind you that if you like our podcast, please subscribe on our website, evoai.ai, and please follow us on Spotify, Apple, Google Play, iHeartRadio, Amazon Music, and Radio Public. Now, let's get back to our episode. Music has always been a vital part of human culture, evolving over time with innovations in instruments and styles. With the advent of the 20th century, technology began to play a significant role in music generation. The introduction of computers in the 1950s marked the beginning of algorithmic music creation. However, the real shift came with the integration of artificial intelligence into music. AI's ability to process data and recognize patterns has made it a valuable tool in music composition. With the rise of deep learning, we've seen the development of models that can understand and generate music with increasing sophistication. Today, AI is not just a tool for composers, but has become an integral part of the music generation process. In this episode, we'll delve into the history, techniques, and future of AI in music. So let's get started. Let's first talk about the mathematics underpinning AI in music. The first one is linear algebra and calculus. Linear algebra, with its matrices and vectors, forms the backbone of neural network operations. Every neuron's output in a network is essentially a matrix operation, or a dot product, followed by an activation function. Calculus, especially differential calculus, it's crucial for understanding the sensitivity of changes. When training neural networks, we want to know how a small tweak in weight can affect the overall error. Backpropagation is the cornerstone of neural network training. It uses the chain rule from calculus to compute gradients, which indicate the direction and magnitude of weight updates. Optimization in neural networks aims to minimize a loss function, which quantifies the difference between predicted and the actual outputs. Techniques used in calculus help find the minimum of this function. Next up, probability and statistics. Dealing with uncertainty is a core challenge in AI. Probability offers tools to handle randomness and make informed predictions. Bayesian networks represent probabilistic relationships between variables. In music, this could mean like likelihood of a note following another. Gaussian processes are non-parametric methods used for regression and classification. In music generation, they can model the probability distribution over possible music sequences, allowing for diverse generation. Another mention here, the Fourier transforms. Fourier transforms break down signals into constituent sinusoids, revealing the frequency component of a signal. In music, this is invaluable for tasks like pitch detection. For instance, identifying the dominant frequency can help determine the musical note of a sound segment. The spectrogram, a visual representation of frequencies in a signal, is often used in AI models for music and is derived from using the Fourier transforms. Next stop, differential equations. These equations describe the relationship between a function and its derivatives. In music, they can model how sound waves evolve over time. Diffusion models in AI, especially in generating audio, use differential equations to simulate the propagation of sound waves, ensuring that generated audio is smooth and continuous. For instance, when modeling the decay of a guitar string's vibration, differential equations can capture the diminishing amplitude over time. What about optimization techniques? The heart of training an AI model lies in optimization. The goal is to tweak the model's parameters to best fit the data. Gradient descent is a first-order optimization algorithm. It adjusts parameters in the direction of the steepest decrease of the loss function. Regularization techniques add penalties to the loss function to prevent overfitting. L1 regularization adds a penalty proportional to the absolute value of weights, promoting sparsity. L2 regularization penalizes the square value of weights, ensuring weights don't become too large. Well, I hope that by diving deeper into these mathematical concepts, you have gained a clearer understanding of the intricate mechanisms that enable AI to generate music. These foundations ensure that AI-generated compositions are not just random notes, but coherent pieces that resonate with us, with our human emotions. Let's talk now about some techniques that are used in AI music generation. Number one, deep learning and neural networks. Neural networks, with their layered architecture, are adept at learning intricate patterns from data. In music, this translates to recognizing rhythms, melodies, and even emotions. Recurrent neural networks, or RNNs, and long short-term memory networks, LSTMs, these are designed for sequence data. In music, sequences are vital, be it the progression of notes or the rhythm. LSTMs with their memory cells can capture long-term musical dependencies, making them suitable for tasks like music prediction or continuation. Then generative adversarial networks, or GANs. GANs operate in a dual mechanism. The generator crafts new music pieces while the discriminator evaluates their authenticity. Over iterations, the generator refines its compositions, aiming to fool the discriminator. Another technique is to use autoencoders for music generation. Autoencoders learn to encode data into a compact form and then decode it back. In music, this can mean compressing a piece into its essential features and then reconstructing it. High-fidelity audio autoencoder. It focuses on preserving the minute details of the original audio, ensuring that the essence of the music remains intact even after compression and decompression. Noise-robust masked autoencoder. In real-world scenarios, audio often comes with noise. This variant of autoencoder can reconstruct high-quality audio even when the input has noise, making the output clear and crisp. Let's talk now about diffusion models versus transformers for audio generation. Diffusion models, as we know, these models simulate a diffusion process, akin to how, if you want, ink spreads in water. For audio, this means generating waveforms by simulating how sound waves propagate. They're excellent for tasks that require high temporal resolution like raw audio generation. Transformers are more general purpose and work by capturing relationships in data regardless of their distance apart. In music, this can mean understanding how a note at the beginning of a piece might influence one at the end. Transformers have been the backbone of many state-of-the-art models in music generation. However, they often work with higher-level representations, like spectrograms, rather than raw audio. The choice between diffusion and transformers. Well, while both can be used for music generation, the choice often depends on the specific task and the desired output. For raw audio generation, diffusion models might be preferred. For tasks that require understanding and generating complex musical structures, transformers might be more suitable. Text to music generation. This is about converting textual descriptions into corresponding music. It's a challenging task because of the abstract nature of translating words into melodies. Gen 1. This model stands out for its ability to generate music based on textual prompts. It can also fill in missing parts of a musical piece or continue an existing one, showcasing its versatility. Let's talk about some specific techniques. These are more specialized methods tailored for particular tasks in music generation. For example, ITTS prompt speech. TTS stands for text to speech. Beyond music, AI can also generate speech. This technique uses prompts to guide the tone, the pitch, and emotion of the generated speech. Speech de-reverberation. Clarity is crucial in audio. This technique removes echoes and reverberations, ensuring the generated audio is clear. Audio caps and wave caps. First one is audio caps, which is an audio captioning technique. Audio captioning refers to the process of generating a textual description or a caption for a given audio segment. This is similar to image or video captioning, but focuses on auditory content. The goal is to capture the essence of the audio, such as events, emotions, or any other significant features in a concise textual format. Then the wave caps that are used for generating descriptive captions for audio segments. The WaveCaps dataset, as detailed in the paper titled WaveCaps, a ChatGPT-assisted weakly labeled audio captioning dataset for audio language multimodal research, is a large-scale, weakly labeled audio captioning dataset. It consists of approximately 400,000 audio clips paired with captions. The dataset was sourced from web sources and the sound event detection dataset. The raw descriptions from these sources were processed using a three-stage pipeline, leveraging ChatGPT to filter and transform them into high-quality captions. Before we move any further, let's discuss about multiscale transformers and multiscale mel-based discriminators. Multiscale transformers are designed to handle data at various scales, especially in the context of music. Music data can range from fine-grained notes to broader musical phrases or even entire compositions. By processing data at multiple scales, these transformers can capture both local and global patterns in the music. Multi-instrument music generation has recently gained significant attention in the research community. Unlike single-instrument generation, multi-instrument generation requires consideration of both inter-track harmony and intra-track coherence. The generation process often involves composing note segments from various instruments into a single sequence. This composition can occur on different scales, such as individual notes, bars, or entire tracks. Most existing research has focused on a specific scale, which has led to challenges in modeling music that has diverse temporal and track dependencies. The paper introduces a multi-scale attentive transformer model aimed at enhancing the quality of multi-instrument music generation. The model employs multiple transformer decoders to learn multi-instrument representations at different scales. An attentive mechanism is designed to fuse information from these multi-scale representations. The key features of this model are 1. The multi-scale representation, which, because the model is designed to capture musical information at various scales, allowing it to understand both fine-grained details, like individual notes, for example, and broader musical structures, like bars or tracks. Another one is the attentive fusion. The attentive mechanism ensures that the model can effectively combine insights from different scales, leading to richer and more harmonious music generation. And the third one is the performance. Experiments conducted on the SOD, which is the Symbolic Orchestral Database, which is in essence a data set used in the domain of multi-generation and analysis, and in conjunction with the multi-track music transformer provides a robust framework for generating multi-instrument music, taking into account both inter-track harmony and intra-track coherence. And the LMD datasets, which stands for the LAC MIDI dataset, in a collection of MIDI files that have been gathered from publicly available sources on the internet. But the primary goal of the LAC MIDI or the LMD datasets is to facilitate large-scale music information retrieval. These two, the SOD and the LMD datasets, demonstrated that this multi-scale attentive transformer model outperforms models that rely solely on single-scale information, both quantitatively and qualitatively. For those of you interested in diving deeper into the technical details or experimenting with this model, the source code and some generated music samples are always available on GitHub. In summary, The multi-scale attentive transformer represents a significant advancement in the field of multi-instrument music generation, offering a nuanced and harmonious approach to creating music by leveraging the power of multi-scale representations. Let's talk now about discriminating and generating Mel spectrograms. Mel spectrograms are visual representations of the spectrum of frequencies in a sound signal as they vary with time. A multi-scale Mel-based discriminator can differentiate between different Mel spectrograms and is also capable of generating them. This is particularly useful in tasks like music synthesis or modification. Let's talk about other techniques. One of them is the MIDI-based generation. MIDI, Medical Instrument Digital Interface, that's what it stands for, is a protocol designed for recording and playing back music on digital synthesizers. MIDI-based generation refers to the creation of music using MIDI data. This allows for precise control over notes, their duration, and other musical attributes. Algorithmic composition. This is the process of using algorithms to create music. Instead of traditional composing methods where a human composes a piece, algorithmic composition involves using mathematical models, rules, or computational algorithms to generate new music. AI-driven interactive tools. These are tools powered by artificial intelligence that allows users to interactively create, modify, or analyze music. They can range from AI-driven music recommendation systems to tools that assist composers in generating new musical ideas. Let's jump now to some real-world examples of AI in music. One is Google's Magenta. Magenta is an open-source research project initiated by Google and is designed to explore how machine learning can be utilized to augment the creative processes. What are the key models and tools that this Magenta has? First of all, Music VAE, which is a tool that can interpolate between musical sequences, creating smooth transitions, and it can also generate musical scores in the style of a given artist. And performance of RNN with this model is designed to generate expressive piano performances. It can capture the nuances of timing, dynamics, and pedaling of piano. Next one is OpenAI's MuseNet. MuseNet is a deep learning model from OpenAI, as we said, but it can generate compositions in various styles spanning multiple artists from Beethoven all the way to Beatles. Some of the features: MuseNet is trained on a vast dataset, allowing it to understand and generate compositions in different genres, including rock, pop, and classical. Next up will be Google's Music LM, which is one of Google's advancements in the realm of AI music generation. Music LM is designed to generate music samples conditioned on text descriptions and audio prompts. It doesn't require self-supervised semantic representation of the prompts, making it versatile in understanding and generating music based on varied inputs. Gen 1's application in text-to-music generation. Gen 1 is a significant advancement in the field to text-to-music generation. Gen 1 can generate music that aligns with the mood and theme of given textual prompts. It can fill in missing parts of a musical piece, ensuring that the added segment aligns with the rest of the composition. Given a starting piece of music, Gen 1 can continue the composition in a coherent manner. Let's talk about OpenAI's Jukebox, which is another example here. Jukebox is a neural net developed by OpenAI that generates music, including rudimentary singing, as raw audio across various genres and artist styles. Unlike some other models that generate MIDI or symbolic music, Jukebox generates raw audio, capturing the nuances of instruments and vocals. Jukebox can be conditioned on lyrics, allowing it to generate songs that align with the provided text. And it's trained on a dataset of 1.2 million songs, enabling it to understand and generate in various styles and genres. And last but not least, Splash Music is an innovative platform that leverages AI to revolutionize the music creation process. It's designed to make music generation accessible to everyone, regardless of the musical background. Just please note that I'm getting this from their website. There is no paper or documentation available to what Splash Music is using, whether they're using transformers or they're using diffusion models. So I'm getting it straight from the website. Splash Pro users can simply enter a text prompt and the AI will craft a song based on that input. That allows for a very high degree of customization and ensures that each generated piece is unique. And Splash's Pro Gen 2 utilizes a generative model that's continuously training. This ensures that the music it produces is of high quality and aligns with the latest trend and styles. Text to vocals Splash is capable of offering text to vocals feature. This allows users to add custom singing or rap vocals to their songs, making the composition even more dynamic and engaging. The platform emphasizes that their generative model is still in training, which means it's continually evolving and improving. This iterative approach ensures that the music generated remains fresh and relevant. Splash Music is not just a tool for individual creators, it can be used in various sectors from entertainment to advertising, providing a quick and efficient way to craft custom pieces of music. With the addition of Splash Music, we now have a comprehensive overview of some of our most prominent real-world applications of AI in music. These platforms and models are pushing the boundaries of what's possible in music generation, offering tools and features that were once thought to be the exclusive domain of human artists. Let's talk now about some challenges in AI music generation. The first one is the challenge of maintaining originality and avoiding overfitting. AI models can sometimes overfit to their training data, leading to generated music that lacks originality or simply mimics existing compositions. A potential solution would be the regularization techniques and diverse training datasets can help in reducing overfitting. Additionally, introducing randomness or noise during generation can lead to more original outputs. Another challenge is ensuring the generated music evokes the desired emotions. Music, as we all know, is deeply emotional, and ensuring that AI-generated music evokes the right emotions is crucial. One of the solutions, well, let's think about it. Well, training models with labeled emotional data or using reinforcement learning where the reward is based on the emotional response can be beneficial. Another challenge, handling the vast variability and complexity of music. Music, as we all know, is diverse, with numerous genres, instruments, and cultural influences. Capturing this vast variability is a challenge. Potential solutions? Using hierarchical models that can understand music at multiple levels, from individual notes to entire compositions, can be effective. Another challenge, generating long compositions with coherent structure. While many models can generate short musical snippets, creating longer compositions that maintain a coherent structure throughout is challenging. A potential solution? Sequence models like LSTMs or attention-based models like transformers, which can capture long-term dependencies, can be used. Another challenge, introducing human-like creativity and nuance is a big problem. While AI can mimic patterns in music, introducing the creativity and nuance that the human composer brings is absolutely challenging. A potential solution could be collaborative AI tools that allow human artists to guide and tweak the AI's outputs can lead probably to more creative compositions. Another challenge, real-time music generation. Generating high-quality music in real time, especially during live performances, is a huge challenge due to computational constraints. Optimized models and dedicated hardware accelerator can aid in real-time music generation. That perhaps is a solution. Another challenge, ethical and copyright concerns. As AI generates music that might resemble existing compositions, there are concerns about copyright infringements and the ethical implications of AI-created art. As a solution, maybe clear guidelines and regulations regarding AI-generated content can help address these concerns. These challenges highlight the areas where AI music generation still has room for improvement. However, with rapid advancements in the field, many of these challenges are being addressed today, paving the way for more sophisticated and nuanced AI-generated music in the future. Let's talk now about the future of AI in music. AI, first of all, has the potential for personalized music generation. AI's capability to analyze vast datasets allows it to tailor music experiences to individual tastes. Platforms like Spotify utilize AI to analyze user behavior, including song preferences, skip rates, and playlist creation. By processing this data, AI can predict and recommend songs that align with the user's musical taste, creating a unique listening experience for each individual. AI allows also for integration with virtual reality and gaming, or at least has the capability of doing this. The immersive world of VR and gaming demands dynamic soundtracks. In gaming scenarios, AI can adapt music in real time based on gameplay events. For instance, during intense battle scenes, the music can become more dramatic, while during exploration, it can be more ambient. This dynamic adjustment enhances immersion and emotional engagement. Let's stop for a second and look at the ethical considerations and the role of human composers in the world of AI generated music. The rise of AI in music brings forth some ethical dilemmas. As AI generates music, questions about copyright ownership arise. If an AI trained on classical composition creates a new piece, who owns that? Additionally, there is a debate about the diminishing role of human composers and whether AI generated music can truly capture human emotion and creativity. Let's look briefly also at audio processing using machine learning. As we know, AI is revolutionizing audio processing. Tools like NSynth by Google use neural networks to understand the characteristics of various sounds and then create entirely new sounds. This has applications in sound design for movies, games, and music production. Another tool, Lander, uses AI to master tracks, adjusting levels and equalization to produce a polished final product. Music composition through AI. Is that possible? As we saw, yes, indeed, it's here and it's now. AI-driven tools are actually simplifying the music composition process. Ava, for instance, uses deep learning to create emotional soundtracks. It's trained on a vast dataset of classical compositions, allowing it to generate music pieces that evoke specific emotions. Such tools can assist composers by providing a base layer, at least, which composers can then, of course, refine. What about music production with AI? As we know, AI's role in music production is expanding now. Amper Music, an AI-driven tool, can handle the entire music production process. It allows users to specify parameters like genre, mood, and tempo, and then AI crafts a complete piece based on those inputs. It democratizes music production, allowing even those without technical expertise to create music. Trust me, I've done it myself. What about songwriting? Yep, I think songwriting is going to be made easier these days. AI is assisting the songwriting process. Tools like Amadeus Code can generate melodies based on AI's understanding of popular song structures. While the current capability of AI in understanding the nuances of lyrics and melodies is still evolving, it is expected that AI will play a larger role in songwriting, assisting artists in crafting hit songs. The changing role of AI in music. The boundary between AI and the musician is blurring more and more. As AI becomes more advanced, there's potential for AI to not just assist, but also to become the primary creator of music pieces. However, music is deeply personal and emotional to all of us, and many believe that while AI can mimic patterns, the true essence of music will always require a little bit of human touch. The intersection of AI and music is a fascinating space, with rapid advancements promising to reshape the way we create, consume, and think about music. While challenges remain, the potential for innovation is vast, heralding an exciting future for the music industry. The integration of artificial intelligence into the music industry has undeniably ushered in a new era of musical exploration and innovation. From the way music is created and produced to how it's consumed and discovered, AI has left its indelible mark. AI's role in the music industry is multifaceted. It has the ability to spot patterns and trends in vast amounts of data, allowing artists to make informed decisions about song promotion. Tools like Lander and Isotope have revolutionized the mixing and mastering process, making it more efficient and accessible, and tools like Stable Audio allow for people with little to no skills to make music using prompts. For those of you who don't know these tools, Lander is an innovative online platform designed to streamline the music production process, particularly in the areas of mastering and distribution. Isotope is a renowned company in the audio technology industry known for its cutting-edge software and plugins that cater to music production, post-production, and audio restoration. While Stable Audio by Stability AI is designed for music and sound effects generation, allowing even those without a technical background to generate music and sound effects. On the composition front, AI's capability to generate original compositions, melodies, and even lyrics based on existing music data is noteworthy. While songs like Daddy's Car might sound eerily reminiscent of the Beatles, it's a testament of AI's potential in mimicking styles and genres. However, the intersection of AI and music isn't without its challenges. While AI can replicate styles and generate compositions, it currently lacks the emotional depth and personal experiences that human musicians infuse into their work. Music, at its core, is a deeply emotional and personal medium, and the human touch is irreplaceable. Ethical concerns also arise, especially when AI is used to emulate the voices of popular artists without their consent, leading to potential copyright infringements. As AI continues to evolve, the music industry will need to address this and other challenges to ensure a harmonious blend of technology and art. In the grand scheme of things, while AI offers a plethora of tools and opportunities for the music industry, it's essential to strike a balance. The future of music should be one where AI complements human creativity, not replaces it. As we move forward, it will be crucial to ensure that the essence of music, its soul, emotion, and authenticity remains intact. Well, that's a wrap of today's episode of Evo AI. We've delved into the fascinating world of artificial intelligence, unlocking insights that are changing the face of business today and tomorrow. But the exploration doesn't end here. There's always more to discover. Well, I'm Bogdan Janku, and this has been Evo AI. Together, we're part of something bigger, much bigger, a movement towards understanding, innovation, and growth. Well, if you enjoyed our journey today, don't forget to subscribe, and please join us again as we continue to explore the future of AI in business. Until next time, keep evolving.